Yeah, thanks for coming. So today we have Mehtaab Sawhney from MIT. So he will be talking about the recent result about the anti-concentration in Ramsey graphs and the proof of the Erdős-McKay conjecture.
Thanks, and thank you for the invitation. So everything I'll be discussing today is joint work with Matthew Kwan, who's at IST Austria, Lisa Sauerman, who's at MIT, and Ashwin Shah, who is also at MIT. So let me define a Ramsey graph for the context of this talk. So a graph G is called C-Ramsey if G has no independent set or clique of size C log n. So in some sense, these are nearly optimal for Ramsey graphs. So in particular, we know by saying the Erdős-McKay bound on diagonal Ramsey that you always have an independent set of at least size half log base 2 of n, and there exist graphs with no clique or independent set of size 2 log n by the probabilistic method. And so given turns out obviously progress on diagonal Ramsey has been hard, and we don't have a great idea of what these graphs look like in general. In particular, there are no known sort of explicit constructions of C-Ramsey graphs. So motivated by this, Erdős and collaborators sort of made a series of conjectures they formulated a number of conjectures regarding subgraphs of Ramsey graphs or induced subgraphs of Ramsey graphs. And in particular, these conjectures sought to show that Ramsey graphs have diverse induced subgraphs. And the reason this is maybe a useful thing to know is that this sort of suggests that any construction has to look very random-like, which maybe makes it suggest that it might be difficult to find explicit constructions. So there are a long list of works in this direction. So maybe the first was due to Promo and Rodel, who proved that so I'm always going to assume G is C-Ramsey. G contains all possible subgraphs. Of size epsilon of C log n. So in some sense, they're universal for graphs of this size. Schella proved that you have many distinct induced subgraphs. So Schella proved there are 2 to the delta of Cn, so exponentially many non-isomorphic subgraphs. Kwon and Sudakov proved that that there are delta C n to the 5 half subgraphs, which are distinguished by the number of vertices and edges. So what I mean by this is you can look at the number of so you look at for every subgraph the number of vertices in that subgraph and the number of edges in that induced subgraph, and it's saying that in any Ramsey graph that you achieve at least a delta C n to the 5 halves values. This is the conjecture of Erdős, Fourier, and Schoch, and Jensen and Kibosh, Long, and Permian. So it is improving on work of Buch and Sudakov, who proved the original conjecture of Erdős. Proved that G contains a subgraph with n to the 2/3 distinct degrees. So, I mean, each of these results is sort of pointing towards a sense in which, if you look at the induced subgraphs of your general Ramsey graph, they're kind of they're sort of very diverse. You either have all possible sizes for small subgraphs or for larger subgraphs. They're distinguished. You have a lot of distinct vertices and edges, or degrees, say. And there are a number of these conjectures, and essentially all of them were answered except for one. So this is the Erdős-McKay conjecture. So if you look at the problem paper, it was posted sometime before 1992. So I think he already calls this an old problem in this. And actually, Erdős offered $100 for it. And what it asks is that if G is C-Ramsey, then for any x in say 0 to some quadratic amount, there is a subgraph. There is an induced subgraph of G. With exactly x edges. So you can specify a number in this quadratic range, and regardless of what Ramsey graph you have, there's some subgraph with exactly this number of edges. And that was the conjecture. And so this conjecture has been pretty well studied. There's actually a number of results. So for instance, for the canonical example, so it's even actually non-trivial to prove this for even the canonical Ramsey graph, which is G n 1/2. So this was proved for G n 1/2 by Culkin, Fries, and McKay. The first result towards the Erdős-McKay conjecture for general graphs was due to Alon, Krivolevich, and Sudakov. Proved. So I think Erdős, when he writes the problem, says that they had some complicated argument that worked up to like log n squared number of edges. So Alon, Gravelich, and Zurkov proved this for 0 less than x less than n to the delta of c. And actually this paper, so this is making some progress towards the conjecture, but also I think this paper is one of the early applications of like dependent random choice, which obviously is quite an important technique. There's work of Guan and Sudakov who proved this improves on Narayanan, Sahasrabudhe, Tomon. That there are quadratically many distinct edge subgraph counts. And finally, there was a very recent paper of Long and Ploroscu, which showed it under, so instead of assuming that your graph, they proved a bipartite analog of this conjecture. But bipartiteness turns out to make a substantial simplification. So I guess at this point, it's clear what the punchline is. The punchline is, okay, the main theorem is that we can prove this result. So theorem, this is joint work with the authors mentioned before. The Erdős-McKay conjecture is true. And in fact, it's true in a very strong sense. Not only can you just find quadratically many edges, you can find essentially all sensible values. So more precisely, so if you're given a C and eta greater than 0, and G is a C-Ramsey graph, with n vertices, and n is sufficiently large as a function of eta and c, then for 0 less than x less than 1 minus eta e of g, there exists a subgraph, there exists a subset with exactly x edges. And implicitly, we're using extremely powerful and maybe one of the most important results in a result of Erdős and Samaretti, which states any C-Ramsey graph is it has quadratically many edges, or in particular is dense. So in particular, given the result of Erdős and Samaretti and the second line of the theorem, the fact that the Erdős-McKay conjecture is true is essentially immediate. So I guess now, if there are any questions, please feel free to chime up during the talk. But I guess if there are any questions about the statement of result, now would be a good time.
Is the stronger form known for G in 1/2?
Yes. So this version where you go up to 1 minus eta, they actually understand what eta needs to be. It's some like it's some Boolean, and I forget exactly. You
Okay.
you can't get all the values, because if you look at the edges minus like 2, the total number of edges minus 2, in a random graph, every vertex has like degree n. So you can't go literally to the edges of G, but they actually understand like what the behavior of eta. I think
Okay.
one can quantify some eta in our result, but it's not. I have no a priori reason to believe it's optimal. Yeah. Okay. If there are no other questions, then at this point, then I think maybe the first perspective change that will happen is really our main result is not actually about this conjecture directly. It's really about understanding the number of edges in random subsets of Ramsey graphs, and really sort of a more probabilistic perspective. So this result follows pretty quickly. I mean, almost essentially immediately from the following sampling result. Given the work of Alain Kerlage and Surkov. So theorem, let G be a C-Ramsey graph and U be a random subset of the vertex set. Then you have the probability. So if I'm studying a random subset, I can sort of look at the random variable, that's the number of edges in the random subset. So this random variable is anti-concentrated. So in particular, the probability that the number of edges in this random subset equals some particular value, this is bounded by at most n to the 3/2. And for any reasonable value, you have a lower bound. So the expected number of edges is, so you're sampling every vertex with probability half to include in your random subset. So it's a random subset. So you expect x to be around the number of edges of G divided by 4. And it turns out the standard deviation of this random variable is approximately n to the 3/2. So I'm going to look at some large constant times n to the 3/2. The probability that my random subset contains this many edges, this is lower bounded by a similar quantity. So this is really about as sharp an understanding as you can hope for understanding this distribution. It's telling you that within multiplicative constants, you understand every. So it's saying in the bulk you achieve every value with the correct probability, the bulk of the random variable. And so if you have this result, then just by applying it, you get subsets with approximately the number of edges divided by 4. And to say prove it for different values of x, what you can do is sort of, instead of looking at the whole graph, take a small subset of maybe 1/10 of the vertices, you will have less edges, and then apply this result and to subsample to find your correct size. So really, this is the heart of the matter. Once you have this, then you have all the results. There's some slight extra technical linear terms, but don't worry about them. They're not so important. So I wrote this for p equals a half. In fact, one can sample each vertex with probability p. With p and like with p just being bounded away from 1 and 0. Right? And the same result holds, but these two results are very similar. We essentially only consider p equals a half with some small tricks. So the real substance of the paper is sort of trying to understand this random variable and sort of treating it as some quadratic form and sort of thinking about how you can understand the local distribution. And in general, tools for trying to understand the local distribution of such random variables. And broadly, many of the tools seem to be pretty general, and even in the paper are sort of written for, let's say, quadratic polynomials of very general types. And sort of where Ramseyness comes in is maybe to guarantee certain conditions on the polynomials that arise naturally. So that's the perspective we'll take, and sort of to do this, it's natural to actually write out this polynomial as a low degree polynomial of some independent random variables. So what we care about, so by definition, this is EG of U. So the expected number of edges in the random subset. And in distribution, or like by definition, this is basically the same as you look at UV, which is in your edge set, and you look at chi U or psi U, psi V, where psi U and psi V are, let's say, Bernoulli 1/2. So these are just the indicator random variables of whether you've included in the set. Turns out that this is not the right basis, or it turns out it's much more convenient when you're working with random variables to sort of have them be normalized. So Bernoulli 1/2 is not a normalized random variable. It doesn't have variance 1 and it doesn't have mean 0. So you can make it that by, you can basically define xu to be chi u minus 1/2 over you can sort of look at 2 chi u minus 1 and define xu. So this is now going to be plus minus 1 with probability 1/2. This is a normalized random variable. And when you do this, you immediately get the following. So you get edges over 4 plus 1/4 times the sum over the vertices P of G, deg dgv times xv plus 1/4 times sum over uv of the edges of xu, xv. And so now this polynomial, which initially seemed quadratic, sort of naturally has two parts. So I mean, okay, there's a constant, which is just the expectation. There's this part, which I'm going to denote the linear part. And this part, which I'm going to denote the quadratic part. And notice that these two parts actually live on very different scales. So Ramsey graphs, C-Ramsey graphs are dense graphs. So they have like order n squared edges. So most of the degrees are order n. So if you do a computation, this tells you that the variance of the linear part is something like order n cubed. But the variance of the quadratic part so it turns out there are n squared terms here because there's something over the edges. And it turns out any two of the like edge terms are their correlation is 0. This is basically what I've done here is called take the Fourier Walsh transform. I've decomposed the function into a bunch of like orthogonal pieces. It turns out the variance of this part is order n squared. So in particular, on large scales, the number of edges in my subgraph is determined by this linear part, and the quadratic part is somehow a lower order term. And so, so therefore, so this actually gives you at least one step towards this result. It tells you something about the bulk distribution of X. So therefore, on global scales, the behavior of X is controlled by the linear part. So if you want to just understand sort of the large scale behavior of this random variable, you can forget about the quadratic part. And if you look at the linear part, well, this is kind of the most classical thing. This is a sum of independent random variables. And so by, say, the Bayesian theorem, we have that X satisfies central limit theorem. So what I mean by central limit theorem here is on the bulk scales, it has the Gaussian distribution. And so given that, well, the main result I told you is I have an upper and a lower bound on the point probabilities, a natural guess would be, does it have a local central limit theorem? And sort of the starting point of the starting point of the technical work of this paper is no. So while you have these upper and lower bounds on the probability, it's not the distribution does not look completely locally like a Gaussian. So in particular, if you take G to be a typical sample of G n 1/2, the distribution actually looks something like this. So these are like the probabilities of the individual points. And there's like constant factor deviations between the probability of a given point and another point, which are, let's say, closer to each other than the standard deviation of the overall random variable. So this is sort of exhibiting extremely wild fluctuations on a probabilistic behavior. And so now, well, okay, why? I think as soon as you see, if you plug this into a computer, this is the thing it spits out, and there are diagrams of this in the paper. You see this and what's happening. So it turns out that there's a pretty, you can use these two facts to understand why is there erratic local behavior. So this is, let's do this kind of slowly. So let's look at the linear part. So we have degree G of u times degree in G of u times xu for u in the vertex. Now assume instead of G in 1/2, we're in a regular graph. A regular graph is Ramsey. So the degree of G is exactly n over 2. Well, then something weird happens, right? This is always in some lattice. It's always in n over 8 times some integer. So the linear part lives on some, is forced to take these values, which are, let's say, omega n apart. And once you have that, then you have the quadratic part to kind of do sort of smooth between these points. But the quadratic part has variance n squared. And so since I have variance n squared, it has standard deviation order n. And so around every point, you get some sort of kind of bump. I don't know, some weird bump. And so basically, because these bumps aren't like wide enough, you can't smooth out the distribution completely. And so because you can't smooth out the distribution completely, you get these really weird spikes. And this is ultimately what's causing this behavior. The fact that the degrees could sort of somehow be structured in a way that you get this lattice, and you can't, and the quadratic part doesn't have enough variance to smooth out the points between this lattice. There's no way to rule it out. So now this turns out to be a really special case. I did something very special in that I said, oh, the degrees are exactly the same, and so you live on a lattice. Turns out it's slightly more complicated in general, but what the critical thing happens is if the degree sequence of G is arithmetically structured, then one can have spikes as above. So then one makes this quantitative through some work. So this is quantified. Using the notion of what's called a regularized least common denominator due to Verschanen in the context of singularity of random matrices. So, okay, so there's a dichotomy. Either you're arithmetically unstructured, and if you're arithmetically unstructured, then it turns out these are arithmetically unstructured, then these spikes don't happen. They don't really happen, and your distribution turns out to be approximately locally Gaussian. If it's not, then you have some arithmetic structure. And what you can do, what you can sort of look at the definition and play with it a bit. What this says is you can break the vertex set into a small number of pieces such that the vertices in each piece have roughly the same degree. Actually, a very similar degree. I'm not going to make this precise, but okay, that sort of is a direct generalization of this example. You would sort of have one bucket in this case, but this example can be made slightly more complicated by having, say, a series of vertices with degrees n/4 and a series of vertices with degree 3n/4. So one needs to make this precise, and this is what, let's say, the least common denominator lets you do. Okay. So, well, by something, you're forced to consider these sort of vertex sets and breaking your vertex sets into these buckets. So I'm going to completely ignore the arithmetically unstructured case. It turns out that is, say, is substantially simpler. So for the sake of simplicity, let us assume that there is exactly one bucket. And that G is regular. That's not a question mark, it's a statement. Okay. So in this case, if you have exactly one bucket and G is regular, when I condition on the number of vertices in the bucket, this really amounts to conditioning on the size of U. And so now you can sort of, well, I mean, if you look at this pretty picture, maybe you look at it and you're like, well, if I condition on U, is it locally Gaussian? So I have removed this kind of funny effect due to having this lattice structure. Hopefully now there's no such obstruction. Well, okay. This is also false. You can look like the following. Sort of, the distribution is extremely skew in some sense, or like it's a bad try. Like it's somehow extremely skew in one direction versus the other. And then you stare at this and what's happening. So what's really happening is, let's sort of pretend that when you condition on the size in this example where you're regular, really all that's left is the quadratic part. So let's look at the quadratic part and ignore that we're conditioning on size. We're looking at something like this random variable, xu, xv, where uv is an edge in G. So there's actually a very powerful tool here if you want to understand sort of the global behavior of this random variable. What you can do is you can imply what's called the invariance principle. This is due to Mosul, O'Donnell, Shavitz in their work on majority is stablest. But generally we need some specialized version to deal with the slice for our cases, but let's just look at the case where xu are just independent plus minus one random variables. What the invariance principle says is that in distribution, it's the same distribution on the left as when you replace this by a quarter times the sum of chi prime u, chi prime v, where uv is an edge, and chi of u are Gaussian random variables. So in particular, instead of thinking about sort of discrete things, if you only care about the bulk distribution scale, you can kind of only think about the Gaussian distribution. And now the issue sort of presents itself. Really, if you write the middle as the write this, what this is chi prime t, where chi prime is some Gaussian vector a chi, and this is basically a completely so you have some condition a is the adjacency matrix of a Ramsey graph, but this is basically a completely general quadratic polynomial of Gaussians, and so there's no reason to expect that it looks like a Gaussian. You can get basically any distribution that it can arise as being a quadratic polynomial of Gaussians. So then you have to do something. And one of the main results of the paper is sort of to prove several results regarding the distribution of quadratic Gaussian polynomials and the small ball probabilities. And there's something to do here. So there are results in this direction known, like the Carberry-Wright theorem under very general assumptions, but we need something stronger than falls out of just completely, like assuming A is an arbitrary matrix. And what we really need is some notion of robustly high rank. This is a buzzword, but let me convince you that rank has something to do with this. So what happens if this matrix A is a rank one matrix? What you end up having is you want to understand the probability that, like, let's say Z1 squared, so Z is just some Gaussian, is less than epsilon. This event is exactly the same thing as the probability that Z1 is less than square root of epsilon. And this scales like square root of epsilon. So what does this mean? If I look at the probability density function of this random variable, so there's no support below 0, but it kind of has a spike tending to infinity near 0. It's in particular unbounded. And that would be bad for us, because if this picture kind of looks unbounded, then you can't have a uniform upper bound, a uniform upper bound on the probability, on the probability density function. So you need to rule this out, this sort of behavior where your quadratic polynomial sort of has unbounded density function. And this can be ruled out under a robust high rank assumption. And it turns out that you don't need this actually for just the adjacency matrix. You need it for the adjacency matrix, which is slightly corrected in some way, because in this discussion above, I assume that X is exactly a Rademacher. In reality, it lives on some, like, you condition on the sum of the Rademachers being something. So this leads to some correction factor. And so you need to prove some, like, adjacency matrix of Ramsey graphs are high rank under block rank perturbations. But with that, okay, so now one needs to make this all rigorous. So in particular, you need to understand, if you're arithmetically unstructured, that, okay, that you have this actual Gaussian distribution, and in the arithmetically structured case, that conditioning on the sizes of these buckets, that you have this distribution. Proving this is actually quite a technical task. You need a lot of work like decoupling theory and Fourier analysis, but with enough work, what you end up getting is one can control the distribution of EG of U down to scales where So what I mean by constant scales is something like within order, you could control the probability that your random variable lies in some set of size OC of 1. And so for the upper bound, this is fine because I can upper bound the probability of hitting a single point by lying in the interval around that point. But we actually need a lower bound, right? We want to construct graphs of any particular type with any particular number of edges. And for this, we introduce a novel version of the switching method. So what are we going to do? Well, so we have our sampled graph G, and it's some set of vertices U. Suppose you have two vertices V, which is in U, and V prime, which is not in U. If you have that, let's say V has a certain number of neighbors, let's say T, and V prime has a certain number of neighbors in the set U T minus 1, then what you can do is you can swap V for V prime, and you'll change the edge count by 1. You need to be a little bit careful, but okay. So this kind of this idea gives you some local way of handling, sort of making small perturbations to the distribution. So when you do the switching method, normally what you prove is between two classes, there's a certain number of ways to go up in every element, and there's a uniform number of ways that it can be reach the other set. Turns out in this sort of probabilistic thing, in rare events, you can't actually control that. But instead, one can control the moments, like the first, second, and say fourth moments of the number of switches. And the way to see that maybe this is believable is that what you can do is sort of condition on the sets of vertices you want to be your switches, and then the rest of the graph you can use you can just use the previous result regarding the number of edges in a small subgraph, and this will give you some control like this. And this turns out to be sufficient. To give a probability lower bound. Yeah. Okay. So with that, it's a little bit vague what I mean here, but sort of you can this is sort of a more average version. Normally in switchings, you need absolute upper and absolute lower bounds. The key point here is it turns out if you do some Cauchy-Schwarz, you can actually get away with a lot less. You can kind of get away with understanding the various moments of the number of these switches, and that turns out to be sufficient. So that's generally the outline of the paper. I mean, it's a long paper, and hopefully I was able to give some sense of what's happening. But with that, thank you. That's all I had to say.
Okay, thank you very much. Do you have any questions?